Okay, thank you. Well, thank you, Jeremy. So I'd like to apologize to the expert for the somewhat elementary nature of my talk here. I wasn't quite sure what this talk should be about, but it's at the end it's a kind of a personal perspective, if you like, on the field of condensed matter. The microphone is just for recording. Okay, I'll try. Yeah. So this is a sort of a personal perspective on the field of condensed matter and about how this particular Nobel Prize fits in the field, really. Okay, so I nominated these guys some 15 years ago, so I don't think that was relevant. We were asked, from time to time we are sent letters, various people in this department must be receiving also nomination letters from the Nobel Committee asking you to send them something. And I had put exactly these three names, which was many years ago. And I got a letter 2 years ago also, and this time I didn't respond at all. Anyway, so it had nothing to do with my nomination. But let's see. So the outline for the talk, first of all, a very quick history of the field of condensed matter and the basic notions as discussed by Phil Anderson, this year's Nobel Prize. And I'd go over the three papers that are cited by the Nobel Committee, and then discuss more recent developments in topological phenomena within condensed matter, which has really become a very hot topic, really, and then end with some summary and conclusions. Okay, so if you like, the antecedents of condensed matter physics can perhaps be traced all the way back to ancient civilizations in Mesopotamia and China and India, etc., and perhaps even to the caveman who discovered that different rocks have actually very different properties. But really, modern condensed no, I think I'm pressing the wrong one. Modern physics of condensed matter in many ways starts after the understanding of the atomic of atoms, basically, and begins with people like Einstein, Heisenberg, Dirac, etc., who put down the fundamentals of condensed matter physics, a lot of which is used to this day. And actually one can argue that one of the key goals of atomic or quantum theory was really to understand the world around us. And indeed, we can do a lot, and one can even argue that one of the most important successes of this atomic or quantum theory was the development of semiconductor technologies. And so obviously this subject goes all the way back to the beginning of quantum theory, but it would be wrong to conclude from here that condensed matter is basically an applied science. So that's one of the key messages I want to give over here. It would be wrong to say that condensed matter is just about applications. Okay, really, as a unified theoretical discipline, condensed matter physics presumably developed in the 50s and 60s. Wikipedia quotes Phil Anderson as saying that it was their group at Cambridge that first called themselves the condensed matter group. Okay, so that was sometime in the 60s, and really things were in the air. And 1970 is the year when Physical Review was split into A, B, C, and D, and in due course of time PhysRev B became the physics of condensed matter. Okay, so we can call this, the age of super specialization. I mean, this age, obviously, everything was together, but now we have separate disciplines almost, particle physics, nuclear physics, AMO, and astrophysics, and in some sense these are much easier to explain and much better appreciated even to people outside the field, but really the physics of condensed matter remains poorly understood, certainly by outsiders and perhaps even within physics departments. Okay, so this condensed matter physics is really driven by many things. First, we have these chance experimental discoveries, which really, if you like, turn rules of thumb upside down. So, for example, high temperature superconductivity, ever since the discovery of superconductivity in the early 1900s, one of the holy grails of the field was to find superconductivity at room temperature, or at least at liquid nitrogen temperature. And over many years, people had developed these rules of thumb, whereby where one should look for high temperature superconductivity, and they involve things like you should stay away from transition metals, and you should stay away from oxygen, and you should stay away from low dimensional systems, and you should stay away from magnetism. These were the so-called Matthias rules after Brent Matthias. And when high temperature superconductivity was finally discovered in the cuprates, it really, all the rules were completely turned upside down. And similarly, quantum Hall effect and fractional quantum Hall effect, these are other examples. People were convinced that nothing new can happen when you apply strong magnetic fields to semiconductors, and then they discovered quantum Hall effect. And just as they were getting convinced that there are rigorous arguments why the Hall conductivity at these plateaus has to be integer, they found that no, they can actually be fractions. So really, I mean, this is of course one of the very important driving forces in condensed matter, that every few years there are these new interesting discoveries which are totally unexpected. Of course, new tools for probing matter play a very important role. If we can and all these are X-rays, neutrons, etc., they are all honored by Nobel Prizes and are extremely important. New materials are somewhat underappreciated, but obviously they are also very, very important, and especially these days people are able to fabricate all kinds of fancy new materials which can host all kinds of new phenomena. But of course, one of the important driving factors of condensed matter remains theory, and this really talk is going to be basically about theory. And I have basically gathered here Nobel Prizes since the 1950s, which one could count as Nobel Prizes given to condensed matter theorists, and these are mostly physics Nobel Prizes. I have just put together 2 Nobel Prizes given in chemistry to iconic condensed matter theorists, really, Lars Onsager and Walter Kohn, but this is basically the list. And many of these, some of these one can clearly identify for very specific singular discoveries, like for example Brian Josephson's Nobel Prize for the Josephson effect, or Laughlin's for the fractional quantum Hall effect. But clearly there are many other things here that really cannot be understood just for a single phenomena or a single discovery like that. For example, the Nobel Prize of Anderson, Mott and Van Vleck, which only makes sense when discussed in the context of the whole field, or that, for example, of de Gennes. And I think this particular Nobel Prize to Thouless, Haldane and Kosterlitz really fits in that category, that one has to really think about it not just as a single piece of physics, but really how it fits into the whole scheme. Okay, so let me get to the basic notions as discussed by Phil Anderson in his monograph. These are the fundamental, if you like, guiding ideas that really tell us how to think about this field as a whole. And of course, the basic idea is that the physics of many particles is extremely challenging, and in general it cannot be understood by simply knowing the physics of individual particles. And Anderson puts down a list of topics in his book, basically, where the first thing he lists, of course, is broken symmetry, which is the idea that many of the interesting phases of matter reflect broken symmetry, which allows very new types of macroscopic behavior to emerge. For example, broken translational symmetry allows a rigidity, instead of a flow to a shear shear perturbation, basically the system can respond elastically. Okay, this shear rigidity is a result of broken translational symmetry. Similarly, broken spin rotational symmetry can lead to macroscopic magnetism. Spontaneously broken gauge symmetry can lead to superconductivity, etc. So broken symmetry is one of the important guiding principles for understanding condensed matter phenomena. The second one he lists is adiabatic continuity, which is really extremely important, because again it's highly non-trivial that we can understand the physics of such complicated many particle system in terms of their microscopic constituents, and it owes a lot to the idea that complicated systems, essentially the physics can be related back to simple limits. So Fermi liquid theory, of course, is a great example, and many of these ideas go probably before Phil Anderson, certainly to Landau and probably to many others. So adiabatic continuity is the idea that a lot of what we understand in condensed matter can be related back to non-interacting systems of fermions and bosons, and even the classical ideal gas. Classical ideal gas is a good model for understanding solutes in a dilute solution and even in a complex biological cell. I mean, so that relating complicated systems to simple one is a very important part of condensed matter physics. Another extremely important idea is that of renormalization, perhaps first brought into condensed matter physics by Leo Kadanoff, and certainly Ken Wilson won his Nobel Prize for the explanation of critical phenomena, and the idea that we have fast and slow degrees of freedom, and eliminating the fast degrees of freedom renormalizes the effective Hamiltonian that describes the slow degrees of freedom, and at the end leads to just a few fixed points which really capture the important long wavelength, low energy degrees of freedom of the system, and there is a great deal of universality, even though we have myriad complex systems. Basically a few fixed points really control most of the important universal behavior. So that idea all goes under this general field of renormalization, and Phil actually lists the fourth topic as topology, and one might be somewhat surprised by this, because really, I mean, in some sense topology is the subject that says that there is no difference between a donut and a coffee cup, or really is the subject of such exotic manifolds like Mobius strip and Klein bottles, and one might ask, what has this got to do with condensed matter physics? Why is this at all relevant? So the point, however, is that topology can underlie stability of particles and excitations, and in fact perhaps in the context of particle physics, maybe Skirm was the first person who tried to understand protons and neutrons as topological kinks in some pion field or something. So topology can indeed underlie the stability of particles. Topology can be a key to stability of an exotic phase. It can be important. Topological excitations can mediate phase transitions, and topological invariants can account for quantized macroscopic properties, and we will see that examples of all these, that indeed these are all valid statements, and topology indeed is an important part of condensed matter physics now. And this year's Nobel Prize to Thouless, Haldane and Kosterlitz, the Nobel committee quotes this Nobel Prize for theoretical discoveries of topological phase transitions and topological phases of matter. I think this whole name really is a very recent name in my view. I don't think this idea of topological phases was present in those days when those papers were written, but it makes sense. And one thing that has become clear more recently is that topological phases may be more commonplace than one might think. Okay, so the first thing I want to do now is to really go over the three papers that were cited by the by the Nobel Committee and discuss their significance really. So, the first one is the Kosterlitz-Thouless theory, and this is about phase transitions in a two-dimensional system, and basically there was an impasse, there was a kind of a contradiction really, or something that people were not able to understand that was pretty serious, and that had to do with the following. There is this theorem, the Hohenberg-Mermin-Wagner theorem, and in some sense anybody who has studied taken a statistical mechanics course, they certainly do the Bose condensation, which is a very simple problem of non-interacting problem, and one knows that in 2 dimension there is no Bose condensation. There is no finite temperature phase transition associated with Bose condensation in 1 and 2 dimension. That is really a 3-dimensional phenomena, and that generalizes actually, that is first pointed out by Pierre Hohenberg. Bose condensation in an interacting system should not happen in 2 dimension, and really by Mermin-Wagner even more seriously, that any time you have a system with continuous symmetry, they cannot develop long range order at any finite temperature. But on the other hand, numerical studies, for example high temperature expansions by Gene Stanley on 2-dimensional XY model, suggested that there was a phase transition. So, how does one resolve this issue, that you have no long range order, but you actually there is some evidence that there might be a phase transition? Well, so what Kosterlitz-Thouless studied was basically this 2-dimensional XY model, which is actually related to various kinds of physical systems, including thin film superfluids and superconductors, hexatics, 2-dimensional melting, Bose condensation, etc. So, in this model, the absence of long range order can really be seen very easily in just the harmonic approximation. So, if we assume that the system is ordered and that phi is the same everywhere, that is the state with lowest energy, and if we just expand these cosines to harmonic approximation, that quadratic model can be completely solved in statistical mechanics, but because that just requires doing some Gaussian integrals, and the absence of long range order simply falls off, because what one finds is that just because of the harmonic approximation, the spin-spin correlation function will no longer be a constant at long distance, but fall to 0 no matter what the temperature. So, basically the temperature controls how slowly these things decay, but at any finite temperature, essentially at long distance, the spin-spin correlation function goes to 0. That is the statement of absence of long range order. However, this is a power law decay, which is clearly very different from exponential decay. At high temperatures, basically in order for spins to be correlated, there has to be interaction that couples, the coupling has to go through neighbors, and depending on how many neighbors you have in between, that many powers of coupling are needed. The correlations always decay exponentially at high temperature. So, between these two behaviors there must be a phase transition, and what Kosterlitz and Thouless argued, that these phase transitions are essentially controlled by vortices. These are the topological excitations. So, if you imagine a vortex basically is a configuration of spins which is smooth everywhere far away from this core over here, but as you go around this vortex core, basically no matter how far away, the spins are defined modulo 2 pi. As you come around, the spin has to come to the same point, but in between it can wind around a certain number of times. Okay. So, basically if we integrate the d phi over this defied or phi d phi dot dl along this gradient phi dot dl along a long contour, basically that will give us a 2 pi times an integer. This integer can be 0 or plus minus 1. So, these will correspond to the vortices basically, because one can easily show that for such a vortex configuration, the energy of such a configuration is divergent, because no matter how far away one goes, in each circle there is a certain cost which only falls off as 1 over r basically as one goes far away, and so summing over all these gives a logarithmic divergence. So because of this logarithmic divergence, such configurations must be absent. However, if we have a vortex-antivortex pair, so one can imagine something which has a winding number or q of 1 and another one that has a q of minus 1. And by the way, these pictures are put, the Nobel site, the Nobel website actually has put out all these pictures as well of vortices and anti-vortex pairs and so on. So if we put together a vortex-antivortex pair, then far away the spins can all point parallel and not have any cost at all associated with the vortex-antivortex pair. And in that case, the energy of this pair, if you like, the cost, the energy is only related to the log of the separation between them rather than the log of the size of the system. So this is now finite. So the idea is that the vortex-antivortex pair must stay bound in pairs until a temperature such that an isolated vortex can actually have a negative free energy. So basically the picture is that at high temperature, basically these vortex-antivortex pairs are bound together in pairs like this, okay, until, so their energy cost was diverging with system size, but their entropy also diverges like a logarithm, because these vortices can be anywhere, and using just the simple idea that the entropy is related to the log of the number of places where they could be, that gives us a log that means that the free energy will be negative above a certain temperature. So basically at this temperature there will be a cooperative vortex and binding transition. That is the simple idea. That is the topologically excitation mediated phase transition. Now this picture of course was much more carefully analyzed actually by Kosterlitz, modeling these vortices can basically be modeled by a Coulomb gas, and he developed the renormalization group picture with temperature and their fugacity as the two important variable, and confirmed this whole, the validity of this whole thing. The two very important things that came out of this was, first, that true superfluid does not require a condensate. A lot of people believed, and in fact I even had some conversations with Professor C.N. Yang much after this work, who still believe that superfluidity or superconductivity requires off diagonal long range order. But what this work really showed is that you don't need true off diagonal long range order for superfluidity. Just power law correlation, power law order is sufficient to have a non-zero superfluid density. And they also showed that basically there will be a universal, this is one of the important predictions of the theory, is that there will be a universal jump in the superfluid density, which was really shown by Kosterlitz and Nelson. And so the idea is that if one superfluid density would jump at Tc from a 0 to a finite value, and this jump must be proportional to the value of the Tc itself. So really if one plots the superfluid density versus the Tc for various systems, they should fall on this particular line. And this was first confirmed by Bishop and Reppe in superfluid films, but there have been many experimental confirmations of this. Okay. So obviously this aspect of the theory is well verified, but I would argue that the theoretical influence of this paper is far greater than just the fact that some of their experimental predictions were later confirmed. I mean, in particular, the idea of vortices as important degrees of freedom, the idea of the Coulomb gas representation, and the idea that you can have power law correlated phases, line of critical points, etc. These have had far greater influence in condensed matter than just the experimental verification in this one case. Okay. Moving on to the second paper is this Haldane conjecture, which is Haldane actually discussed another impasse, another kind of a contradiction which had not been recognized by others really, which he himself resolved through topological considerations, and this was discussing the antiferromagnetic spin chains or quantum Heisenberg model. So, if we consider this model over here, first written down by Heisenberg in the 1920s, really almost immediately after the discovery of quantum mechanics, and the antiferromagnetic model is one where the spins like to align anti-parallel. It is well known that or one can easily check that for such a model of quantum spins, simple antiferromagnetic state is not an eigenstate of the problem. But Bethe was able to solve the one dimensional problem exactly almost right away by a very famous ansatz, which also has had enormous influence on the field, and people by 1980s when early 1980s when Haldane's paper was written, the properties of this model had been the spin half model had been studied in great detail. People knew that they had power law correlations, there were gapless spin excitations, etc. The spectrum, everything had been studied in detail. On the other hand, what Haldane pointed out that basically what one would expect on general grounds, that a quantum system in one dimension should map on to a classical system in 1 + 1 dimension, and basically this quantum system should have if you like a Lagrangian that looks like this, that basically is that of a nonlinear sigma model, an O3 nonlinear sigma model in 1 + 1 dimension, and in fact one can also by semi-classical methods for large S systematically derive such a Lagrangian. And however, again renormalization group treatment of such a model suggests that this model should have a finite correlation length and a finite gap. Okay, so for example, studies by Polyakov and others shows that if we consider an O3 nonlinear sigma model in 1 + 1 dimension, it should actually be disordered. It should not have power law correlations and gapless excitations. So how can this be consistent? Okay, so Haldane's work was sufficiently controversial at the time. This is known as the Haldane Conjecture. He was not really able to publish his paper. I mean, the only publication that he had was in Journal of Applied Physics, which was the proceedings of the magnetism conference really. Only about 5 years later he was able to publish this in PhysRev Letters. So the reason what Haldane conjectured basically is that this, when we write this term over here, we are missing something, and what we are missing is this additional term that one can write down in the in this Lagrangian describing the 1 + 1 dimensional configurations, and this is really a topological term. He called it a topological term, and again this picture is taken from the Nobel Committee website. If you imagine all the spins far away pointing up, it is a term where the center is actually pointing down, let us say. So if we consider a configuration like this, and if you evaluate the integral of this term over this entire configuration in suitable units, this integral must always be an integer. Okay, and it turns out that so that is the reason for calling it a topological term. It cannot change gradually. The integral of this over the entire space-time configuration must be an integer, and what Haldane noticed is that the quantization, this quantity is defined in such a way that every space-time configuration basically gets a factor. If we are thinking in terms of this partition function as a sum over configuration with some weight, this I means that basically you have e to the I times some 2 pi times some constant or pi times a constant, that for every spin configuration you either get a weight which is minus 1 to the power q, q being the integral of this object, and this q is always an integer for integer spin, but q is always an even integer for integer spin, but q can be even or odd integer for a half integer spin. So for integer spin it does nothing. The partition function is completely unchanged by the addition of this, but for half integer spins it actually can cause interference between different configuration and it can change the physics. So basically he argued that integer spin chains are the ones where the nonlinear sigma model physics that we discussed by renormalization group is valid, because this part simply does not do anything, but for half integer spins, for example, the case that was solved by beta, this interference is important and it leads to gapless excitations. So, basically again this Haldane conjecture after many years was verified. It's verified in many experimental systems, and really computationally it has been quite convincingly shown to be valid. But really in my view the thing that really nailed it completely, removed any doubts about the validity, was these two mathematical theorems. They played a more important role in my view than experiments and computational techniques. One is this Lieb-Schultz-Mattis theorem, and the other is something that existed long before Haldane's paper, and the other is this Affleck-Kennedy-Lieb-Tasaki AKLT model. So the Lieb-Schultz-Mattis theorem basically just says that half integer spins are very special and they must have either degenerate ground states or gapless excitations, but one knows that the ground states are not degenerate. There is especially for spin half chain, there is other Marshall sign rule etc. that tells us that there is actually a unique ground state. So there must be gapless excitation, they have to be there, but this theorem is completely silent about what happens in integer spin chains. Okay, but the Affleck-Kennedy-Lieb-Tasaki model, they actually then proposed an explicit model for which one can trivially write down the ground state, and one knows that these ground states have all the properties that Haldane was conjecturing. And the model basically it requires simply adding to the Heisenberg term a biquadratic term like this, and this now can be written as a projection operator, and one can show that the exact ground state of such a system consists of, so basically one can think of the spin 1 object as a symmetrized, as two symmetrized spin half objects, one of which then in this in the ground state of this is coupled into a singlet to its right neighbor, one is coupled into a singlet to its left neighbor, and basically there is a unique translationally invariant ground state in the system. Okay. Yes.
The uniqueness of the ground state for the spin half chain, doesn't that depend on whether you have an odd or even number of elements in the chain? I mean,
yes, okay,
odd,
right, that is true. Yeah, that is true. If you, I'm sorry, yeah, so it would be in any sector. I was thinking of a SZ equals 0 sector, which means you have to have even number, you are right. Otherwise the Kramer's degeneracy will come in. Thanks. So this model also has this interesting property that if you put a boundary over here, there will always be a free spin at the end. So it has a gap in the bulk, but anytime there is a boundary, at the boundary you have a gapless spin half excitation. So it is now being called an example of a symmetry protected topological phase, one of the first examples of that type. Okay, the third paper, which in some sense is more closely related to the more recent work on topological materials, has to do with the quantum Hall effect, the Thouless-Kohmoto-Nightingale-Den Nijs paper, the TKNN paper. It has to do with the quantum Hall effect and its why it is so accurately quantized. So basically the phenomena of quantum Hall effect is that in a strong magnetic field, if we have a two-dimensional electron gas, then we see these plateaus in the transverse resistivity and vanishing of the longitudinal resistivity, which when one calculates the conductivity tensor, basically the conductivity is quantized in units of E square over h. Okay, that won von Klitzing the Nobel Prize. One knows from again from elementary physics that in crossed electric and magnetic fields charges drift, and so Hall conductivity can simply be related to the density of carriers and the charge of the carriers, etc. And this quantization one also knows from first year graduate quantum mechanics that in a strong magnetic field one has these Landau levels which are highly degenerate, and these quantization really corresponds to having integer filled Landau levels, and the Fermi energy can be pinned really between these due to the sample edges where these Landau levels bend in this particular way. But why should it be so accurately quantized? I mean, okay, Bob Laughlin gave a very clever flux threading argument, adiabatic argument for the quantization of the Hall conductivity, which is a valid argument, that basically if we imagine passing if we first turn our Hall bar basically into a cylindrical surface like this with a magnetic field coming out, and then pierce a Aharonov-Bohm flux through this adiabatically, starting from the value of 0 and going all the way up to a full flux quantum. This is a purely adiabatic flux. So by the time, so the system, the energy levels would change in between, but when you have a full flux quantum you can gauge it away and it shouldn't have any impact. The only change that can happen in this whole process is really that an electron can be taken from this, an electron can be removed from here and brought all the way over here. That is the only possible change. And if you, once you accept this argument that all that has happened is that delta Q is n over E, that delta Q in turn can be written in terms of the current in this direction times dt, which can be expressed in terms of sigma xy, and d phi dt basically can be related to the electric field that has been generated by the Faraday effect essentially. So it right away leads to this condition that sigma xy must be an integer multiple of E square over h. So this is a very general argument, but it hides the microscopic details that really goes into what is the mechanism for this deep quantization. And in particular what TKNN really asked is, what role does the periodic potential play? We know that there is these electrons are not moving in some vacuum, they are actually moving in a periodic potential. And developing a band theory for a inner magnetic field is complicated, because once you apply a magnetic field, the translation operators along x and y do not really commute. But if your magnetic field is rational, that is, if the magnetic flux per unit cell is actually a rational number, then one can choose a big enough unit cell through which the magnetic field is actually magnetic flux is an integer times the magnetic flux is an integer times the flux quantum. Then they do commute, the translation operators along x and y for that unit cell, they would commute, but what that would result is that if you plot on this axis the flux and in units of the flux quantum, and on this axis the energy levels, then the one band will be split into many bands, and the number of bands it will split into will depend on the rational fraction basically. So the band theory of in a magnetic field is extremely complicated. This is known as this Hofstadter butterfly, actually, this beautiful picture. Well, what TKNN showed is that the Hall conductivity can be expressed, the Kubo, just the standard linear response theory, the Kubo formula can be expressed as an integral like this, which in a more modern language is nothing but the integral of the Berry curvature, and I will discuss the Berry curvature I guess in the next slide. It is an integral of the Berry curvature over the entire Brillouin zone, which they argued must be an integer, and in a more modern language this is related to the integral, this integral is related to the Chern numbers, but I do not want to go into that nomenclature here. But this does make the connection to perhaps the single most important theorem in topology, the Gauss-Bonnet theorem, that says that the integral of the curvature of a surface, of a closed surface over the entire closed surface must be equal to 4 pi times 1 minus g, where g is the genus, is related to number of holes. And we all know this theorem, at least for a sphere. The Gaussian curvature is just the product of the 1 over the product of the two radius of curvature. So it is just 1 over r square d2r for a sphere, that just is 4 pi. And if we have a cylinder, we know if we have a torus we know can be just gotten from folding a cylinder which has no internal, or just a plane basically which has no internal curvature. So that should give you a 0. So basically this is the integer valuedness of this one is obviously very closely related to the integer valuedness of this particular quantity here. And indeed this is somewhat well, this certainly influenced the recent developments in the subject of topological band theory, in which Charlie Kane and Suchen Zhang played a very important role, and earlier Duncan Haldane, and it all fits together rather well in context of the work by Michael Berry on Berry's phase. So basically I want to very briefly introduce the idea over here. So first of all, we know in a crystalline material we have this band theory, and the Brillouin zone where the set of k values are defined is always a torus because it repeats in all directions. So the Brillouin zone is a torus, and the point is that the bands can have non-trivial topological properties in the Brillouin zone. And the way we can understand this is, first of all, so what the bands are, that for every, so k is a translational symmetry guarantees that k is a good quantum number, and for every k basically we have a set of states with a set of energies, and let us order them in some way. Then these states of course are only defined modulo a unitary transformation. They are only defined, they are not, I mean, in the sense that there is a gauge symmetry, but there is an additional symmetry. We can choose the unit cell to be like this, or we can choose the unit cell to be like this. We have our choice, and depending on this choice this actual state would change. Okay. So in the language of mathematicians, this is a fiber bundle. Fiber bundle is basically a fancy name for a product space. Our base space, if you like, the k is a torus, and at every point of the torus we have a bundle, we have a set of states, set of occupied states that we would like to talk about, and that is locally like a direct product space, but it could have non-trivial topology. Actually, to give a better example, the simplest example here would be if our base space is a circle and the fiber is basically a line, then the topology could be that of a simple belt or a cylinder. That would be a trivial fiber bundle, but the topology could be that of a Mobius strip. Any region of that Mobius strip is just like a piece of a belt or a piece of a cylindrical surface, but there is clearly a twist in that when there is a Mobius strip there. Okay, so in that sense this fiber bundle could be trivial or non-trivial. In a similar way, bands could have a non-trivial topology basically. Okay, so it all fits in really. I think the correct language to use is that of Berry curvature. So first of all, one can define a Berry connection or a vector potential, which is really how these states change from one k value to another k value. Okay, so this is related to the gradient of the overlap of the gradient of the state at one k to the next k. Okay, this defines, this quantity is gauge dependent, it's dependent on this unitary transformation, but what Berry emphasized of course was closed line integral of these, which is related to the phase system will pick up under adiabatic transformation, which in turn can be related to the Berry curvature. So just like in electromagnetism, vector potentials are gauge dependent, but magnetic fields are not. Similarly, we can define here the curl of this Berry connection, which is then called the Berry curvature, and the TKNN index was basically nothing but an integral of this Berry curvature over the entire Brillouin zone. Okay, and that they argued must be an integer. Okay, so what Charlie Kane realized is that in strong spin orbit coupling, basically even without a magnetic field one could have these interesting curvatures and interesting topological effects basically, and this was called a two-dimensional topological insulator. The simplest way to understand this two-dimensional topological insulator is by analogy with the quantum Hall effect. So quantum Hall effect, magnetic field of course gives a directionality. All the electrons want to circulate in a particular way, okay, so they become chiral, if you like, they all go this way, and the edge states of a quantum Hall system are basically all circulating in a particular direction. This circulation is what gives us the very nice quantization of the Hall conductivity. In contrast, if we have no magnetic field, but we have strong spin orbit coupling, it is like we have time reverse pairs which can have opposite circulation. Okay. So, chirality of one set of spins is like this and the other spin is like this, but they have the same kind of thing. They are insulating in the bulk, but they have these conducting states on the surface, and what Sucheng Zhang and others realized is that this should lead to this quantized spin Hall effect, which was observed by Molenkamp and collaborators. So basically this is an experiment where they measure the conductance along a particular direction, and when the system is not in this, when the system is not basically is not a topological insulator, the insulating phase has essentially zero conductance, this showed by this picture over here, but when they tune it to have this topological phase, then in where it is supposed to be insulating, it instead gets a conductance which is given by twice E square over H, and this factor of 2 represents the fact that you have 2 conducting channels which can carry the current in this direction over here. So 2 ballistic edges basically. Okay, there are, of course, there is a lot of interest in many sort of related systems. The subject has really exploded, topological band theory. For example, there are these very interesting Weil semi-metals which among other things show the physics of chiral anomaly, well known in particle physics, happening in condensed matter systems. A very interesting possibility which one can also lump within the topological band theory idea if we accept BCS approximation, that is, superconductivity simply amounts to adding to the electron hopping term a pairing term, and simply a bilinear pairing term. So that makes if you like a superconductor basically a system of non-interacting fermions where the underlying fermion degrees of freedom are mixtures of particles and holes, are sort of superposition of particles and holes, and these kinds of systems can have even more interesting fermions which are their own antiparticles, for example, and Sergey here is an expert in that kind of physics. So this is obviously a very active research area. My interests are actually more in sort of emergent topological phases which cannot be related to any kind of band related physics. They are not related to the physics of non-interacting fermions. So this goes beyond the fractional quantum Hall effect is one example, but there is a lot of interest in spin models, and this year's Buckley Prize actually has been awarded to Kitaev and Xiaogang Wen for the study of such emergent topological phases which are not related to bands, energy bands basically. So actually the simplest context in which one can understand some of these really, although this subject has been around for a long time, very important contribution was made by Alexei Kitaev by introducing simple toy models in which one can easily understand the physics of such emergent topological phases. So the really nice model is this so called toric code model, which is a model again of spin half quantum objects which live say on a square lattice. One can consider any 2-dimensional lattice, but let us consider a square lattice, and let us imagine putting spin half quantum degrees of freedom on every bond of this lattice. And Kitaev introduced 2 kinds of interaction. One is a plaquette interaction. It is a product of sigma z operators on all the 4 spins of the plaquette. So, because all sigma z's commute with each other, basically all these bond operators are obviously going to commute with each other. They also have the property that their square is equal to 1. So, their spectrum is just plus minus 1, they are kind of trivial. Similarly, the second operator that he introduced are these vertex operators. So, let us consider any vertex. It is a product of sigma x operators on all the bonds that are that connect to that particular site, the vertex basically. So, these sigma x's, the a's, they also commute with each other, but furthermore the a's and b's commute with each other. That is the simplicity of the model, because if we consider any one a and any one b, then either they have no spins in common or they have 2 bonds in common. So, in any case sigma x's anti-commute with sigma z. So, pair of sigma x always commutes with a pair of sigma z, and so the result is that the whole Hamiltonian has a trivial spectrum. Each one of these can take values plus or minus 1, they all commute with each other. So, it is a very, very simple exactly soluble model, but it is a remarkable model. It is remarkable in that if we consider this model as a part of some large system in the bulk, basically it has a unique ground state, because one can show first of all that if we think of representing in terms of say the bonds where sigma x values are plus 1 or minus 1, that only closed loops must be present and the amplitude for any closed loop can be related to any other closed loop. Basically one can show that the ground state is essentially unique as long as you are considering such a system in a bulk. But the moment you have a system on a non-trivial topology which has loops that cannot be contracted completely, for example on a torus you find that you have multiple ground states. You on a torus for example the system has 4 degenerate ground state. If you have a surface with 2 holes there will be 16 ground states, etc. So, number of ground states is related to the topology of the system, and not only that, these if one another way to think about these systems is basically to punch holes in a 2-dimensional lattice, and around every hole if you like there will be 4 ground states, 4 possible ground states, and I am calling them ground states, but in a model which deviates from this exact model one can also think of one of them as the ground state and others as excitations, and these excitations basically have interesting topological properties. They behave like anyons, they acquire interesting phases as you take them around each other and so on. So, it is very simple model but extremely rich physics, and an important question really is, does this actually how would one look for such a physics in a more realistic model? How would we know that we have such a model? So, let me not go into this in the interest of time over here. Okay, I just wanted to mention that Xiaogang Wen is another champion of this overall idea that perhaps is a very interesting one. Can everything we know emerge from entanglement of ordinary quantum bits? What kind of excitations can such models realize? So, what one can show is that one can realize electrons as coming out of quantum bits, one can show that one can realize electromagnetic fields, I mean one can realize photons as coming out of these quantum bits. There are also people arguing that you can even get space time arising out of entanglement of quantum bits. So, perhaps this Xiaogang Wen is a big champion of the idea that we are in the middle of a new quantum revolution associated with information. Information is reality, and everything that we know of can perhaps be understood as emerging out of entanglement of ordinary quantum bits. Okay, so my interest is primarily in the question of whether such emergent quantum spin liquids arise in real materials. Okay, so what are the examples where what are the real spin systems or magnetic systems where such physics can actually arise? So, one such system is this quantum spin, well, the spin ice system also has received a lot of attention as a system in which even at the classical level one has monopole, magnetic monopole type excitations with interesting properties, but in presence of quantum fluctuations there is a possibility, at least theoretically one can write down models where one should have emergent quantum electrodynamics with photons and so on. So that is one very exciting area. Another one is this Kagome lattice antiferromagnet, which is a potential candidate for Z2 spin liquid, that is quantum spin liquid where the emergent gauge degrees of freedom are Z2 valued basically. Okay, so whether these things actually happen in real materials is still an open question that has really not been settled, and this will be partly the subject of my talk tomorrow. So finally, to conclude, basically we have seen that there's been an enormous influence of, this is about topology more than field theory really, there's been an enormous influence of topology in condensed matter physics. The influence of field theory is much much better documented obviously, and this was a well deserved Nobel Prize for Thouless, Haldane and Kosterlitz. The recent discovery of topological band theory also holds significant promise. I mean, the people are dreaming of all kinds of interesting devices and applications based on them, and there's a very interesting question about whether there are interacting topological phases beyond the fractional quantum Hall effect, which I would argue is well established really. And ever since this Nobel Prize was announced, we had certainly a debate in our department about whether this closes the door on future Nobel Prizes in this field or whether this opens the door for more Nobel Prizes. So some people argued that basically this Nobel Prize was awarded to Thouless, Haldane and Kosterlitz because of the recent work on topological band theory and so on, which obviously has made this field much more central, but I would argue that their work was really very important to begin with, and I am very glad that the Nobel Committee decided to honor them first. But in my view really this opens up the possibility of many more Nobel Prizes in this field for the work that has already been done, and certainly for more experimental discoveries such as Majorana fermions, such as new devices based on the physics of topological materials such as quantum spin liquid phases, etc. So I am much more optimistic that this is actually a positive sign. It is not closing the door on previous work, but rather opening the door for them. Thank you.